My last video showed how I got started with the Tang Nano 9K FPGA development board. In this video, I want to start doing something with it. FPGAs contain a lot of lookup tables used to realize combinational logic and flip-flops to store data in registers, but they also have hard IP blocks for more specialized functions, such as phase-locked loops, oscillators, memory blocks, and arithmetic units. In this video, I'll try multiple Verilog modules, hardware arithmetic units, simple serial communication with a Raspberry Pi, and both combinational and sequential logic. My design goals are to have the FPGA implement four things: 3 registers, A, B, and C, to be able to reset the register values to 0, to implement the math operation C equals C plus A times B, and to be able to serially write to A and B via a data in signal and serially read C via a data out signal. These will be controlled by a clock and 2 command signals driven from the Raspberry Pi. When designing, it's good to use familiar and standard components such as shift registers. They are commonly used to convert between serial and parallel data. I'll create Verilog modules for a serial in, parallel out shift register and a parallel in, parallel out shift register. A and B will be stored in 2 PIPO shift register instances and C in a single PIPO instance. 4 signals will manage all of the operations. AB-INA enables the A and B registers to receive clock signals. C-INA does the same for C. PLD commands C to do a parallel load on the rising clock edge rather than a serial load. Reset causes all enabled registers to be set to 0 on the rising clock edge. I could have had the Raspberry Pi drive these 4 control signals, but it's better to use only 2 command signals and have combinational logic derive the 4 controls from them according to the Boolean formulas shown. The table shows how the commands are realized. Consider the reset command encoded by 00. It enables A, B, and C and sets reset to tell them to reset to 0 on the rising clock edge. The sum command enables only C and tells it to do a parallel load, thus storing a new C value on the clock rising edge. The new value comes from the plus block. You should be able to see how A and B are written and C is read by studying the diagram. Note that reading C causes its bits to be cycled around, leaving them in their original positions when the read is complete. Here's a picture of the hardware setup. There's a Raspberry Pi 0W on top, and you can see the 5 signals plus a ground wire running from it to the Tang Nano 9K. The Tang Nano is powered and programmed via its USB-C port. This diagram shows which pins are used on the Raspberry Pi and the Tang Nano. I don't understand the details of this, but FPGA pins 35 and 52 appear to be special. They can use the internal clock routing paths inside the FPGA. Pin 52 connects to a 27 MHz external oscillator on the Tang Nano board. I don't use this because the Raspberry Pi is providing the clock to the FPGA in this design. But if I use a pin other than 35 for this, the EDA tool complains that clock routing will be suboptimal. So use pin 35 when you're connecting an external clock. Before diving into the Verilog for the FPGA and the C for the Raspberry Pi, why don't we see them working together in action? So here in this window, we have the program that interacts with the FPGA. This is running on a Raspberry Pi 0. And we can run it by just saying sudo mac command. And if I type help, it shows a list of commands that it supports. So reset sets the registers on the FPGA to 0, so A, B, and C become 0. Read reads C and shows that it is indeed 0. Write sets the A register and the B register. So I could say 2, 2 to set A and B both to 2. And then sum does the math operation. So it sets C equal to the old value of C plus A times B. So 2 times 2 is 4. So if I do that operation, C should become 4 because 0 plus 4 is 4. Now, A and B are still 2 and 2. So if I do another sum operation, that will add another 4 to C. So 4 plus 4 again, and C will become 8. So I could change A and B to something like 2 and 3 for 6. And so now if I sum 2 times 3 plus 8, I should get 14, which I do. And if I do a reset again, that would set all of the registers to 0. And we can see that. So, I mean, that's an example of the Raspberry Pi commanding and exchanging data with and interacting with the FPGA. So next we need to look at the Verilog on the FPGA and the C on the Raspberry Pi, but I think we should start with the FPGA. Here's the Gowin IDE that we saw in my last video. So let's open Project Mac FPGA, the one we're using. And we see that the project has 3 Verilog files and 1 constraints file. The constraints file determines the FPGA pins that the project will use. The top level module is Mac FPGA. So if we open it up, one of the first things we see is this parameter width, 16. And what that's doing is determining the width of shift registers A and B, and then C will be instantiated to be 2 times 16 or 32 bits. So I think it would be a good idea if we proceeded from the bottom up. So let's look at the shift registers. So this Verilog file implements the serial in, parallel out shift registers. And the parameter works like this. The instantiating module can override the value. This 16 is just a default, but the other module actually determined it in this case. The heart of the implementation of the shift register is these output registers here. These synthesize as D flip-flops, and they provide the storage of the shift register. So there'll be 16 of them because of width. And the other inputs are a clock signal, a reset signal, and the serial in signal. So in the synthesis, the D flip-flops are the things that pay attention to the clock. So this code down here determines what happens on the rising or positive edge of the clock. So if reset is 1, then the D flip-flops that form the shift register are all set to 0, so that clears them to 0. If reset is not 1, then this statement here determines what the D flip-flops will get set to. And these curly braces mean concatenation. So what this is doing is forming 16 bits, with the high order bit being SN and the 15 lower order bits being determined by this. So you can see that this is in effect doing a shift, in fact a shift to the right. Now let's switch to the parallel in, parallel out shift register. And you can see that it's kind of similar. Once again, this output reg statement here is what causes the D flip-flops to be synthesized, and they hold the value of this shift register, which by the way is shifting to the left. And this one is actually synthesized to be 32 bits wide, because that's what the synthesizing module that we looked at first did. And so it has the same clock and reset and SN inputs as the previous shift register, but it has another input, which is PIN, and so that's 32 bits wide, and that's providing the data for setting it when it's in parallel mode. And this control signal here, PLD, is what determines that. So if PLD is true, then the value of the shift register will get set to the values that come in on the signal's PIN. And once again, the shift registers are the things that are clocked. And so this if determines what happens on the rising edge of the clock. Like before, if reset is 1, the registers are cleared. But now, if reset is 0 and PLD is 1, this happens. The D flip-flops take the values from PIN. That's a parallel load. And if PLD is not 1, then P out is set according to this shift pattern, a left shift. So SN is in the least significant bit position. So it's similar to the PIPO shift register. But I want to make a comment. This if statement looks like it's like an if statement from a normal software programming language. But Verilog synthesizes to hardware, which acts in parallel. So it's not right to think about this as doing this check, then this check, then this check. But it is right that the action is sort of prioritized. So if reset is 1, it is true that P out will get set to 0. And if reset is 0 and PLD is 1, this action will occur. So it's interesting to ask how the synthesis can create a circuit that is not sequential, but still achieves this parallelization. And the Gowin schematic viewer tool can be a help there because it shows us what the synthesis output is. So this is the parallel shift register, and you can see it's complicated. These are the 32 data flip-flops. So what I did is in a separate project, I instantiated a 3-bit wide PIPO shift register just so we could look at it. It's a lot easier to read if there's only 3 of the data flip-flops. So let's take a look at that. Here is how the Gowin IDE tool synthesized the shift register whose Verilog we just looked at. And I have to admit that this tool in some ways isn't very good. It tends to use the same color for different networks and also doesn't put dots to show where they actually connect. And it doesn't do a very good job of showing when a net is actually consisting of multiple bits, which subsets of the bits go from one place to another. So it's often produces things that aren't very readable. So I've taken this one and annotated it. I've changed the color of some of the traces, and I've added some additional labels that I hope will make it a little bit more clear. So as we said, the shift registers are really represented by D flip-flops. And so here are the 3 D flip-flops that make up this shift register. Remember we said that we instantiated a 3-bit version. So 3 D flip-flops. And notice that they're the only things that are paying any attention to the clock. So the clock signal is here in green, and it goes to all 3 of the flip-flops. And so those flip-flops are going to capture a new value in their data port on the rising edge of that clock, as D flip-flops do. And the interesting part of this is all of these muxes. And these muxes are what the if turned into. And so if you don't know, a mux is something that uses a control signal here on the bottom to select which input becomes the output. So on this mux here, if the control signal is a 0, the top trace becomes the output, and in this case goes on to be the input of the next mux. So let's start to get an idea how this works. So trace the reset signal, and notice that what that's doing is it's becoming the control signal of the rightmost 3 muxes. And also notice that this mux is driving the data input for this flip-flop, this one for this flip-flop, and this one for this flip-flop. So whatever the rightmost muxes are outputting is what's going to get stored on the rising edge of the clock. So if reset is 1, that means that it uses the lower input on all of these muxes. And that lower input is tied to 0, which is hard to see in the diagram that the Gowin tool produces. But these are all just tied to 0. So when reset is high, no matter what these other muxes are doing, it doesn't matter, the value that will be stored in the D flip-flops is 0. Remember, that was the highest priority and first case in the if. Now, if reset isn't true, then the value stored in these muxes is the output of the leftmost muxes. And so let's take a look at that. The second highest priority thing was PLD. So if PLD is true, then we're supposed to do a parallel load. And notice that the PLD signal is the control signal for the leftmost muxes. So if it's 1, the bottom input is the one that's passed through, and that is Pin. So that's how Pin becomes the value of the P out registers when you do a parallel load. Now, the more complicated case is when reset is 0, PLD is 0, and then what's happening is that the value that's going to these registers is, or these flip-flops, is the upper input of all of the leftmost muxes. And so where do those come from? So take a look at SN. That becomes the input of this topmost mux on the left, and that becomes the value of the low order bit in the shift register. And what about the other ones? They're shifting values from one D flip-flop to the other. So for the shifting pattern that we want to happen, the old value of this D flip-flop has to become the value of this D flip-flop. So how can that happen? Well, this output is going like this and snaking around like that. and then going into the input of this mux, and thus becoming the value of this T flip-flop. And then similarly, the output of this one is snaking around like this and going to this mux and becoming the value of this T flip-flop. So that's how the shifting happens. Before returning to the Verilog, let's take another glance at the Mac design and make a sort of mental list of things to look for in the Verilog. So first of all, it has to define the signals that are going to communicate to the Raspberry Pi, and those are shown in blue in this diagram. It also has to instantiate the shift registers A, B, and C. It has to implement the combinational formulas that form the needed control signals, and it has to gate the clocks to the shift registers so that the E and A signals work, so those AND gates. And it has to implement the math operations as shown here. And finally, it just has to, in general, wire the components together. So those are the things to look for in the Verilog. So back to Verilog, let's open the top level module. And the signals that communicate off the FPGA and thus to the Raspberry Pi are defined here as the parameters of this top level module. So we see our command clock D in, D out. And you can also use the LEDs that are on the Tang Nano board itself. And I do that sometimes for debug purposes, but that's commented out here. And the module instantiations occur here, as we had said before, and their widths are determined by this. And also there's a syntax for connecting signals in this module to the I/O signals or the interface signals of the modules. So for example, this PIPO shift register has a interface input SN, so that connects to DN in this module, with DN being defined up here. And let's see, we have to look at how the control signals are formed. That's combinational logic. And so these assign statements just essentially create combinational logic blocks that do the right thing. So the operators are expressed in the select notation, for example. That's a bitwise OR, a bitwise AND, and a bitwise NOT. So it's very easy to form those control signals. The clock gates are similar. That's just ANDing the enable signals with the clock that's coming as an input to the whole module, and that forms the clocks that go into the shift registers. So you can see those assigned up here in the instantiation. See AB clock going to clock and C clock going to clock of the PIPO module. And let's see, the arithmetic is also very easy to do, and it's kind of acting in a combinational way as well. So that's forming a signal sum out that always has the value of A out times B out plus sum in. And that looks just like it did in the design diagram. Some more debug stuff here commented out. And the last thing to look at is just in general how things are wired up. And so to do that, you can declare wires in the Verilog and then just use them in these assigns or in the associations that are created in the module instantiations. So that's how the top level module works. It's actually pretty simple. And now a quick look at the constraints file. So again, that's associating the interface signals of the top level module with pins on the FPGA. And so you can see these pin numbers correspond to what I presented at the beginning of this video. In particular, remember we used pin 35 for clock. Also notice that I've chosen pins that are all 3.3 volt pins on the Tang Nano board. So we specified their type as LVCMOS 33. So that's all there is to the constraints file. Now let's take a look at the C program that runs on the Raspberry Pi. And the first thing to notice is that it's using the PIPO library to set into read GPIOs, and that's available on multiple versions of Raspbian. And then here at the bottom of the main function, there's a little command parser that does commands. So for example, if you type reset, it'll call command do reset. If you type write, it'll call command do write, pass A and B to it. So let's take a look at do reset. And you can see it's very simple indeed. All you have to do is use the GPIO APIs to set the command pins to 0, 0, and then cycle the clock, which basically means wait a little bit, set the clock to 1, wait a little bit, set the clock to 0, and wait a little bit. And this A, B, C ref stuff is the program keeps track of what A, B, and C should be. I was using that as a debug aid. So cycle clock is right above here, and you can see that we're just using GPIO write to control the clock pin. So it's really simple. So now let's look at do write. And so that pass in as functions A and B, which are to be written to the FPGA. You set the commands to 0, 1. And then set val to a 32-bit variable, which is essentially containing both B and A. And then the idea is that we have a loop here that essentially sets D in to the bits of A and B successively and cycles the clock. So that's how they get sent on the pin that the FPGA reads to receive A and B. So you can see that this program is really quite simple, and I'll put it on GitHub so you can look at it in more detail if you want at leisure, but I won't spend any more time on it. So that's my first project using the Tang Nano 9K. I think it's quite useful for learning about FPGAs and Verilog. I may change the project to use only a single bidirectional data line and maybe even implement an I2C slave. I'll make a video if this proves interesting. I'm also interested in exploring more of the hard IP blocks in the Gowin FPGA, such as the oscillator, memories, and other clock-associated things. I'll make videos if that proves interesting. But I think I'll end this video here. Please look below for GitHub links to the source code. Thanks for watching.